I already have other podcasts on emissions from cement, steel, aluminum, and so on, but I don't get tired of them. So whenever I think there is some new result, I try to produce a little podcast out of them. This paper came out in 2022, so not that new, but this is about global iron and steel plant CO2 emissions and carbon neutrality pathway. It will just run through very quickly. I'll read the abstract just so that we have the main points, and then you can skip if you don't want to look at the figures. The highly energy intensive iron and steel industry contributed. Sorry, this actually came out in 2023. It was submitted to the journal in 2022. I should clarify that. The highly energy intensive iron and steel industry contributed about 25% of the global industrial CO2 emissions in 2019. Usually you don't have data up to date, and is therefore critical for climate change mitigation. You want to make these industries as as low emission as possible, if not zero. Despite the discussions of decarbonization potentials at national and global levels, plant-specific mitigation potentials and technology-driven pathways remain unclear, which cumulatively determines the progress of net zero transitions of the global iron and steel sector. So when a country commits to net zero, it's looking at its emission sources and trying to reduce emissions and enhance sinks and so on and so forth. But that's at an aggregate level. What happens when you look at sector level? Let's say here we develop a CO2 emissions inventory of 4,883 individual iron and steel plants along with their technical characteristics, including processing routes and operating details such as status, age, operation years, etc., which obviously determine the total emissions even though they are all producing iron or steel. We identify and match appropriate emission removal or zero emission technologies to specific processing routes, or what we define thereafter as a techno-specific decarbonization roadmap for every plant. So it is going down to that scale, saying you are running this technology and this processing, and this is the age, this is the status in terms of efficiency may drop with age, for example. So how do you work at that individual factory level? We find that 57% of global plants have 8 to 24 operational years, which is the retrofitting window for low carbon technologies as well. Low carbon retrofitting following the operational characteristics of plants is key for limiting warming to 2 degrees C, whereas advanced retrofitting may help limit warming to 1.5 degrees C, but this is a claim that I would verify. If each plant were retrofitted 5 years earlier than the planned retrofitting schedule, this could lead to cumulative global emissions reductions of 69.6 gigatons of CO2 with a huge uncertainty of plus minus 52%. So that's where you have to be careful about 1.5 versus 2. So that's for 2020 to 2050, almost double that of CO2 emissions in 2021. So cumulative global emission reductions will be double that of global emissions in 2021. Our results provide a detailed picture of CO2 emissions patterns associated with production processing of iron and steel plants, illustrating the decarbonization pathway to the net zero emissions target with the efforts from each plant across the planet. So that's where the innovation is. It's not aggregating over a region within a country, but is going down to plant level. So you can see plant types strewn across the world, lots in China, India, US, Europe, and then you have quite a few in South America and Southeast Asia, but generally less so in Africa and Australia. So there are various types: coal and BOF. You can follow up on the details. There's like an electric arc furnace, for example, here, and so there are various furnaces which use different types of fuels and different emission levels, of course. Right? Direct reduction of iron, so there are processes of how you convert iron ore to the feedstock for the furnace and so on. So all those things are considered here, and I'm not going to go into details because that level of detail is not of interest for general audience. So maps of iron and steel plants CO2 emissions in 2019, and they are iron and steel plants located in China, Iran. So we'll look at further maps which correspond to these legends of or numbers of A, B, and so on and so forth. And what details do you need? If you look at different regions, you see how the combination of various types of fuels running the iron or steel plant are mixed within a given country, like India, for example, or China, right? So that's kind of a detail that you can look up if you're interested. But what are we looking for? Did I do that correctly? That's figure 1. So figure 2 here, total output in terms of millions of tons. So coal, charcoal fired iron and steel plants, and you have operation years here, other types of iron and steel plants, and total output in terms of million tons of CO2. You can see the differences here in the total output here and the total output here, and here again different countries. And you have the legends here in terms of age distributions, youngest ones to the oldest ones. You can assume that oldest ones are not performing as effectively and efficiently as possible, and their emissions are going to be higher. Okay, so CO2 emissions and iron and steel output from global plants in 2019 by region, age, and operation years. I won't go into the details again, sorry about that. So we are looking at CO2 emissions, and there is not a surprising result there. Depending on how old you are, your emissions are higher and so on. And you have total output in terms of millions of tons of iron or steel, so that's also important, because efficiency factor per, let's say, ton of steel or iron, how much are you emitting? That should also account for something, right? So keeping that in mind, there is a range of things in terms of age, output, and emissions. And where would you get, if you continue to operate in this way, in terms of cumulative mitigation of CO2 emissions from iron and steel plants, assuming different improving strategies from 2020 to 2050? So these are again cumulative emissions. You can see the range from low numbers to high numbers, because it depends on the time horizon you are looking at. This is from 2020 to 2030 without intervention, 5 years of the retrofitting to make it more efficient and less emission or emission reduction is delayed 5 years, or there is a default retrofitting and 5 years ahead retrofitting, which means you are beginning to reduce emissions through process, through technology and other pathways. So you can see the types here again: electric arc furnace, gas injection, gas based, oxygen plants, charcoal, coal based, and so on and so forth. So in the first decade, 2020-2030, you are already in 2024. So without intervention, you will have 32.6 gigatons in terms of emissions. So this is cumulative mitigation, which means that's how much you have to reduce. 5 years late retrofitting, what you get, let's read this carefully just to be sure we are saying it correctly. Cumulative mitigation of CO2 emissions from iron and steel plants, assuming different improving strategies from 2020 to 2050. So expected emissions and emission reduction. So A to C are maps showing cumulative emissions from all plants without any intervention for 3 periods, namely 2020. So you have ABC here: 2020, 2030, 150, 2020 to 2050. So this is the total. We split into 2 periods. So this is the cumulative emission. Okay, and you have the mitigation potential. If you have, so what are we looking at here in D2 DG? Sorry, that's arranged in a strange way. ABC and then DEF. So you have to be careful how you read it. Okay. For 3 periods, D to I, maps showing results by periods, rows of panels. So you're going DEF JKL. I'm forgetting my alphabets. Okay, so again, just kind of jumping ahead, depending on when you retrofit and what the retrofitting is, whether it's default or whether it's ahead and so on. So there is usually a policy or a scenario or a plan, a strategy that's in place. So you are either going to get delayed in implementing it, or you're going to stick to the timeline, or you're going to get ahead of it somehow. So obviously you can see the natural results that the mitigation is going to be affected by that. So you can see here mitigation of million tons of CO2 per year, what you are expecting in terms of different types of iron and steel production, and if you are on time, what you get less than somewhat. If you are delayed 5 years, you don't see much difference, but actually there are differences. But if you are 5 years ahead, then you per year you get higher mitigations, and you get a jump here as well. You can see the evolution for different types, so you have to be careful which is benefiting the most. The orangish color here is the charcoal furnace, charcoal blast furnace. So story is simple, that there are choices to be made when you go down to plant level across the world. Each plant has a specific pathway to reducing its emissions and mitigation potential out to 2050. And the point is, aggregating is not going to be very useful. So if you look in terms of remaining CO2 emissions budget under the 2 degree C or 1.5 degree C climate limits, and cumulative CO2 emissions from iron and steel plants under different scenarios. So now you are going into different levels of warming, 2 degree C, 1.5 degree C, and you are looking at late retrofitting versus without intervention, default retrofitting without versus without intervention, 5 years ahead retrofitting versus without intervention, and the best case scenario, 5 years ahead retrofitting, so you have carbon capture, utilization, sequestration plus hydrogen as energy source, versus without intervention. So you can see the numbers and where you end up in terms of the low carbon options, and you can see the scales are same in both annual CO2 emissions in gigatons, but where you hit zero is going to be very different. So here you have low carbon, yellow and green, and here you are hitting here around, let's say 2040, and here you are hitting much earlier. So these are scenarios, and these are options being calculated for each plant based on the parameters that we talked about in terms of status, age, process, right? So just to read off again, status, age, operation years, etc., and then the energy source, coal versus electric arc versus hydrogen, and so on. But having done all that, it should be noted that adopting CCUS as well as hydrogen based steel making in the same plant may not substantially increase emissions mitigation potential compared with adopting only one of the two technologies. In their calculation, adding CCUS and H2 doesn't make much of a difference versus just using CCUS or H2. Both add value, but not together. They don't enhance much in terms of total potential. So in this study, you have selected the CCUS technology with more maturity and potentially less cost. So some optimization has been done as the representative deep carbonization technology too. I have ants running up my legs. In a tropical country, it's a rainy season, so you get snakes, ants, all kinds of insects coming out as well. People are reporting snakes coming out and being caught and so on. Yay, exciting, right? So in this study we have selected the CCUS technology with more maturity and potentially less cost as the representative deep decarbonization technology to discuss in detail the importance of deep decarbonization in the global iron and steel industry for the realization of net zero climate targets from 2020 to 2050. It's a trajectory you need to be on to hit net zero by 2050 as a whole. Of course, China said 2060, India said 2070, and many countries have not committed, and so on. But the idea is very simple. Deep decarbonization is basically, here, for example, we are talking about going to each plant and tracking emission sources like status, age, process, etc., and working at that level as opposed to saying everybody will use more H2 or more electric arc furnace or direct ion conversion and so on, DRI and so on, direct reduction and so on and so forth. Okay, I found it to be useful, so I'm being very brief and skipping a lot of details, but you can go and follow up if you're interested. It's a very nice paper with a lot of references as well if you want to follow up. Okay, see you in the next big idea.